Wait, is that, who's that? Is that Gautam? Yes. Okay, good. All right. So, so in the last class, we started talking about contamination issues, both naturally occurring contaminants in groundwater as well as anthropogenic sources of contamination. So we listed a few of them, and then I've shared uh, a podcast. I think I sent an email a few hours back, which incidentally appeared, you know, right after our previous lecture, which was discussing this particular aspect. And I think they spent a lot of time trying to understand this nitrate contamination in groundwater, specifically coming from agricultural runoff or return flow, right? And so that coincidentally, we were speaking about the same thing yesterday or in the previous class. So I thought that was interesting. So the point that I wanted to make was um, what we spoke yesterday was in the context of groundwater alone. Now, this problem is not limited to groundwater. It's present both in surface water and in groundwater. And as if you also get a chance, please listen to that podcast because it spends a lot of time in discussing the nature of the problem and the potential issues that can arise from nitrate contamination in water bodies. Okay, so please spend some time on that, and so it's a serious issue which needs to be addressed. And so what we'll try to do is we are not going to spend from here on, we are not going to be spending any time talking about a specific contaminant. We are only going to talk about general processes that govern the transport of these contaminants. Okay, so it could be any of these contaminants. The transport is governed by the same fundamental processes. Okay, all right. So we also then spoke a little bit about the different processes by which some of this pollutants which enter the surface groundwater or the surface water bodies can be naturally degraded. So that's a fancy word over there, attenuation. Attenuation is just another way of saying degradation or reduction of pollution, right? So there are these different processes that allow the pollutant to naturally be degraded over a period of time, right? Either by dilution or by adsorption or by some kind of chemical reaction which reduces the concentration of the pollutant, or microbial decomposition, or just simple physical filtration, right? All of these processes, of course, it varies the efficacy or the extent to which these different processes can work on any particular contaminant depends on the nature of the contaminant, right? So if you don't have uh, for example, a contaminant with large particle size, this filtration cannot work. Okay, or if I have a contaminant which does not react with any of the existing minerals that are present in the groundwater or in the subsurface, then chemical reactions are no longer possible. Similarly, adsorption may not always work with every different type of soil, or every contaminant may not adsorb on different surfaces. So therefore, the extent to which these different processes can degrade the pollutant, of course, will vary from one situation to the other. Okay, all right. So now we are going to move on and talk about uh, the transport of these contaminants. And please remember that we are not speaking about any particular contaminant. We are talking about the general idea of how any of these contaminants can get transported in water. And again, when I say okay, I shouldn't even say water. It's also commonly applicable to air as well. Through any fluid, if contaminant is getting transported, these are the processes that govern the transport of that contaminant. Okay, so there are three major processes that typically govern the transport of contaminants. One, advection. I'll talk a little bit about that. The second process is molecular diffusion, and then the third process is mechanical dispersion. Okay, so advection is when the contaminant simply moves along with the fluid, right? So the fluid is moving with a certain velocity, and if the contaminant is present um, in that fluid, it simply moves along with the fluid. That process is referred to as advection. Some people also call it convection, but that is more relevant if we are referring to heat, right? But in general, in the context of contaminant transport, we prefer to use the word advection, which refers to the transport of the contaminant or the movement of the contaminant along with the fluid. Okay, that's the first and probably the most major process that governs contaminant transport is advection. The second process, molecular diffusion, is some kind of random Brownian motion that happens, right? So this molecular diffusion is a random Brownian motion. So it's basically at the scale of uh, the molecule, right? So that's why we can call it molecular diffusion. So we have this random motion of these pollutant in the water or in the fluid, which is also one mechanism by which the contaminant can get transported from one place to the other, right? This, please remember that these three processes add on to one another. There may be advection happening simultaneously. Molecular diffusion may also be happening, right? So it's not that one of them happens and the other isn't happening, right? If advection is happening, molecular diffusion, of course, is some kind of random molecular motion at a very, very fine scale. So that's always happening. Whether advection is happening or not, molecular diffusion is always happening, right? And then the third process that governs transport of contaminant is mechanical dispersion. Now, this mechanical dispersion is you can call it uh, you can say that it's not necessarily a fundamental process. It is uh, you can say that it is an outcome of the fact that we are unable to quantify the velocity of the fluid or the contaminant at every point in space and time, right? So for example, if I'm trying to predict the motion of a particular contaminant in groundwater. Now, do I know the velocity of groundwater at every point in space and time in that particular aquifer? It's impossible for me to know. In time, it's impossible. In space, it's equally difficult, right? If not impossible, right? So the velocity of the fluid that's moving is not known to us at every particular point in space and in time. Now, when that is the case, what we do is that instead of representing the velocity at every point in space, we come up with some kind of an average velocity that is representative of a particular region in space. Okay, so for example, uh, if I want to know uh, the velocity of a contaminant moving in a particular direction, we figure out using uh, Darcy's law or whatever it is. We figure out the Darcy velocity, which is the flux per unit cross-section area, and then you divide it by the porosity of the soil sample. That gives you some kind of a representative pore water velocity. But does it mean that every single uh, water particle within the pores of that particular soil is moving with that particular velocity? It's not possible, right? I'll just give you an illustration. Now let us just imagine. So let us say there are some soil particles over here. Okay, I'm just going to draw some few random soil particles all over the place. Okay. Now let's imagine that I have some contaminant. I'm going to draw a few different particles of contaminant which are on one side of this, and the flow is happening from left to right, let us say. Okay. Now, what I will do is I'm going to track these particles in space. Okay. So let us say this particle moves around these and ends up here. Okay, this particular particle probably tracks a different path and then ends up here. Okay, this particle might follow another path, whatever it is. Okay, I'm not able to go exactly in between the soil particles, but anyway, you understand what I'm trying to do. Okay, so the final, the particle started off at a particular point and they've all traversed, let's say, a horizontal distance of L. Okay, let's say they've all traversed a certain distance L. Is the distance covered by each particle exactly the same? Obviously not, right? Because each one is tracking a different path depending on the nature of the particles that are arranged in this particular setup. Each particle is going to follow a different path, and although the distance traveled by them is the same, the time taken for each particle will be different, which means the velocities that the particles have experienced over that distance is going to be different. But do we really know the velocity at this level of detail? We don't. We will typically be talking at a much higher scale. We are probably going to say that the velocity between here and 100 meters away, the velocity is, let's say, on average 1 centimeter per day or 15 centimeters per day, something like that. But that 15 centimeters per day is representative of all of these different particles, right? So although in reality, each particle will experience different velocities, all of these particles will be given one representative velocity because we are unable to find out all the different velocities that the different particles are going to experience, right? So the outcome of all of this is that in reality there is a velocity variability, right, which we are unable to uh, accurately characterize. Okay, and when my contaminant travels along with these fluid particles whose velocities are unknown to us, so what will happen is that these different particles will get dispersed, right? So if I'm looking at this particular example, for instance, right, maybe this first contaminant particle, maybe it reached here at time t1, let's say. Okay, and this one reached after 10 minutes, let's say t1 plus 10 minutes. This one reached at t1 plus 3 minutes. This one reached t1 minus 2 minutes, something like that. I'm just making up these different points. So what does that mean? They all started at the same point at the same time, let us say, but they don't reach the same distance at the same time, right? So what is this? This is basically what you mean by dispersion. When you say the crowd has dispersed, what does it mean? There's a big crowd of people, and then when they disperse, they all move in their own directions at their own speeds, and then they all disperse. That's what we typically say when we say crowd disperse. Something similar in the case of these contaminant particles, which are all moving with their own velocities, which we do not know. And since we are unable to characterize that velocity variability, it translates into what is referred to as mechanical dispersion. Okay, the reason we say it's mechanical is because each particle is still moving with its own velocity. Okay, and this dispersion simply is referring to the fact that the different particles are going to be, even if they start at the same point in space and time, they do not travel the same distance in the same amount of time. They each take their own times. They each travel their own distances, and therefore, as a result, even if they start off together, they end up getting dispersed. Okay, does that make sense? Any questions on this? That's okay. You're looking for the microphone? All right. Okay, I'm assuming that it's more or less clear. Okay. So now mechanical dispersion is basically our way of acknowledging that we are not able to characterize the velocity at every point. If we know the velocity at every point, there is no need for mechanical dispersion. But because we will never be able to know the velocity at every point, therefore, there is this process that we introduce, which we refer to as mechanical dispersion, which is basically an outcome of the fact that we do not know the velocities that the different particles, the different uh, contaminant particles are going to experience, right? So that is mechanical dispersion. Okay, all right. Now we'll just spend a little bit of time on this, the process molecular diffusion. How many of you have heard of Fick's laws of diffusion? Anybody's heard of it? Yes, you have, Vicky. Thumbs up, or you have. Okay, I can't see your thumb. Oh, you haven't heard of it. Okay, fine. Okay, so Fick's laws of diffusion, basically there's Fick's laws are basically two. Okay, so first law of diffusion, Fick's law of diffusion says something like this: F equal to minus D times dou C by dou X, right? So this diffusion, what this Fick's first law says, I'll probably say one here. This is Fick's first law. It indicates that this diffusion is proportional to the concentration gradient, right? I've written this in one dimension. You can also extend this to 2, 3 dimensions, whatever it is, right? So dou C by dou X is basically the concentration gradient. C is the concentration of the contaminant, and dou C by dou X reflects the how much the contaminant concentration is varying in the X direction, right? Which means basically the contaminant will move from higher concentration to lower concentration, right? When the contaminant diffuses, it moves from higher concentration to lower concentration, and which is exactly why you have, similar to Darcy's law, you have that negative sign in front of the on the right hand side, right? So it's minus D times dou C by dou X. Remember when we wrote Darcy's law, we said Q, the Darcy flux, is minus K times dou H by dou X, right? Where the flow goes from high head to low head, high total head to the lower total head. Similarly here, I have dou C by dou X, and the diffusion happens from high concentration to low concentration. So therefore, this dou C by dou X will be a negative term. To account for, to take care of that, we put that negative sign in front of this, in front of the term, which converts it to some kind of a positive rate at which diffusion happens. And this D, this constant of proportionality that we've introduced, is basically called the diffusion coefficient. Okay, so now if I were to look at the units of, what are the units of concentration? What are the units of concentration? Concentration is kg per meter cube or milligrams per liter, right? ml minus 3. Okay, and then I have dx in the denominator, so that's L, another L. Okay, is there a question?
Milligram per liter.
Milligrams per liter. Yeah, thank you. Kg per meter cube. Yeah. So C has got units of ml minus 3, and then I have another L in the denominator, so that's ml minus 4. Now the F on the left hand side, that's my diffusive flux. Okay, so the F is basically the diffusive flux, right? So diffusive flux is basically the mass uh, uh, per unit time per unit cross sectional area, right? So the left hand side has got dimensions of m, l minus 2, t minus 1, right? Mass per unit cross sectional area l minus 2, per unit time t minus 1. On the right hand side, I have dou c by dou x, which is m l minus 4, right? So this is m l minus 4, dou c by dou x, the entire term. So therefore, the diffusion coefficient d must have units of L square t minus 1. For this equation to be homogeneous, the diffusion coefficient d must have dimensions of L square t minus 1, right? So uh, uh, meter square per day or meter square per second, something like that. So that's going to be the diffusion coefficient. Now, Fick's second law is kind of an extension of first law, and it basically takes care of the concentration changes in concentration as a function of time. So it looks something like this: dou c by dou t, dou c by dou t equal to, I'm going to introduce a new term, d star dou square c by dou x square. Sorry. Okay. So dou c by dou t, the rate of change of concentration at a particular location, equal to d star, which is sometimes this d star is referred to as the effective diffusion coefficient. Okay, so there's not much of a difference between d and d star. Don't worry about it. So d star is the effective or the apparent diffusion coefficient, and dou square c by dou x square. Now again, if you look at the units on the right hand side, I have, what do I have? M L minus 5 for the dou square c by dou x square, and then dou c by dou t will be m l minus 3 t minus 1, right? So m l minus 3 t minus 1, and then here I have m l minus 5. So this d star, the effective diffusion coefficient, again will have dimensions of l square t minus 1. So d and d star basically pretty much mean one and the same thing. Okay, so that's the Fick's laws of diffusion. We are not going to be able to spend more time on this, but we'll probably use this. Uh, uh, Maybe you might learn about it in some other course, or probably in your air pollution course. If you take it, you might encounter this again. Okay, all right. So what is typically done is that instead of looking at this mechanical dispersion and molecular diffusion as two individual processes, what is typically done is to combine the impact of these two, mechanical dispersion and molecular diffusion, combine them into one process, and that is sometimes referred to as hydrodynamic dispersion. Okay, so I'm again introducing a lot of new terminologies, but don't worry about it. So what it is telling us is that both dispersion and diffusion, what they are doing, whether it is mechanical dispersion or molecular diffusion, the impact is to spread the contaminant, right? What does molecular diffusion do? From regions of high concentration, the contaminant moves to regions of low concentration, which means what? It is going to spread. Okay, and mechanical dispersion, because of this velocity variability, has the exact same impact, right? So instead of having two separate processes written in this way, it has been felt that why worry about these two processes as if they are completely different from each other. Why not just include them into one process? So that is what we refer to as this hydrodynamic dispersion. So the total flux due to hydrodynamic dispersion, so I'm going to call it H disperse, is basically a combination of the mechanical dispersion and the molecular diffusion, right? So these two together uh, gives me the total flux that happens due to this new process that I'm introducing, which I'm going to call hydrodynamic dispersion. Now, this molecular diffusion, we had a what is that dispersion coefficient, which we call d star. Okay. Now suppose I have suppose I come up with another. I'm going to call this the longitudinal dispersion coefficient. Don't worry about the L. I'll get to that shortly. But now let us think a little bit about this mechanical dispersion. Okay. When you say velocity variability, let me ask you a question. Now let us say I have a running race. Okay. Uh, Suppose I have a running race with which is over a short distance. Let's say a 100-meter race. Okay. In a typical 100-meter race, what do you think will be the time difference between the winner of the race and the person who comes last? The time difference between the winner and the person who comes last, will it be a long time or will it be a short time? Long or short? We'll have to learn sign language, right? The race is short, 100 meters. Now suppose I increase the duration of the length of the race, 200 meters. Then what happens to the time between the winner and the last person who comes last? Increases. Relative to the 100-meter race, the 200-meter race will have a greater distance between, greater time between the winner and the person who comes last, right? If I now move on to an even longer race, let's say a 400-meter race or an 800-meter race, the person who comes first and the person who comes last, the time between them will increase. Okay, and then at the extreme, if I have a marathon, right? If 100 people run the marathon, the person who comes first will finish in 3 hours or 4 hours, whatever it is. The person who comes last may take 7 hours or 8 hours. So there'll be a huge time difference between the person who finishes the race first and the person who finishes the race last. Now relate this to the speed with which the runners run during these different races. In the 100-meter race, everybody is trying to run as fast as possible because it's a very short distance, right? So all of them are running at about the same speed. I mean, assuming that they are all of more or less equal capabilities, right? They're all running at about the same speed, 30 kilometers per hour, 35 kilometers per hour, whatever it is, right? But as the length of the race becomes longer, the top speed of the participants keeps reducing because you can't sustain your top speed for longer and longer distances. So in a marathon, typically, you are probably running at a very low speed compared to a 100-meter race, right? So which means the spreading of the participants during that race is directly proportional to the velocity with the average velocity with which the people are running. Does that make sense? The higher the velocity, the less the spreading between the different runners. The lower the velocity, the more the spreading between, right? Now, you will have to, this analogy works perfectly well for a running race, but when it comes to this mechanical dispersion, it's the exact opposite. This mechanical dispersion is directly proportional to the velocity, the average velocity, right? So therefore, this mechanical dispersion we will use rather than this d star diffusion coefficient. For the mechanical dispersion, we will use what is called, okay, maybe I'll write it on this side. So this velocity with which you're running, let's say Vx, the average velocity with which the different people are running, is proportional to this mechanical dispersion coefficient. Okay. Now, what should the units of this be? Based on whatever we have done now, this has to have units of L square t minus 1, right? This is what we had in the previous slide as well. The diffusion coefficient has units of L square t minus 1. Okay, and the higher the dispersion coefficient, the more the dispersion among the different particles of the contaminant. Okay, and I'm saying that that is proportional to the velocity. So the velocity is, of course, has got units of Lt minus 1. So we need, so the constant, okay, now the constant of proportionality, unfortunately, it's also an alpha. Okay, so this d mechanical dispersion is equal to, I'm removing this proportionality symbol and I'm replacing it with an alpha. So that's kind of a coincidence anyway, right? So this alpha L is referred to as the longitudinal dispersivity. I'm throwing a lot of new terms today. So what? Okay, dispersivity means the extent to which the contaminant is going to disperse. Okay, it's a measure of how much the contaminant can disperse. Okay, that's its dispersivity. I'm adding another word in front of that. That's longitudinal dispersivity. Longitudinal means if the flow is happening in a particular direction, then the particles will get dispersed in that direction, which does not mean that the particles will not get dispersed in the direction perpendicular to that. Now remember, when I talk about uh, you know athletes in a race, human beings are they're just going to keep running in one direction, but a contaminant doesn't care about direction. It will just disperse in any direction possible, right? So even if the velocity is predominantly going in one direction, there may still be some dispersion in other directions as well. So that is why you have to distinguish between longitudinal dispersivity, which means dispersion in the direction in which uh, the contaminant is moving, the major direction. There may also be some dispersion in other directions, right? So for example, now just imagine this. Suppose I take a glass of water. Okay, the water is stationary. If I drop some ink into that water, into that glass of water, now that diffusion is going to happen in all directions, right? Now imagine that instead of a glass of water, I put this drop of ink into a river that is moving in a particular direction, right? Now this drop of ink is going to disperse. It will disperse more in the direction in which the river is flowing, right? Because a drop of ink that drops into that river will get transported along with the river and it will start dispersing. But it does not mean that it will not disperse in the other direction as well. The majority of the dispersion will happen in the direction of flow, but some dispersion will also happen in the direction which is perpendicular or orthogonal to this direction of flow. Okay, so the dispersion that happens in the direction of the flow is called longitudinal dispersion, and the dispersion that happens perpendicular or orthogonal to that is referred to as transverse dispersion. Transverse. Okay, so the majority of the dispersion is going to happen in the longitudinal direction. So we will first deal with that. The transverse dispersion can be expressed in some senses using using some kind of anisotropy ratio. If longitudinal dispersion happens to some extent, then the transverse dispersion can be 1/10 of that or 1/100th of that, and so on, right? So we don't have to really get into that. Okay, so anyway, so this hydrodynamic dispersion results in or is the combined impact of these two processes, mechanical dispersion and molecular diffusion. So I'm going to denote this with dl, which is the uh, longitudinal dispersion coefficient, which is going to be alpha L times Vx, which takes care of my mechanical dispersion, plus d star, which takes care of my diffusion. Okay. Now, fortunately, what happens is this d star, this diffusion, uh, as a process, it is comparatively much smaller in magnitude in relation to whatever happens due to mechanical dispersion, right? So for all practical purposes, you can ignore the impact of molecular diffusion and simply say that my dispersion is going to be simply due to, no, I could, to be more precise, I'll put an approximately equal to, right? So this D dispersion is proportional to or equal, almost approximately equal to alpha L times Vx. Now this alpha L, as I told you, is the longitudinal dispersivity. It has dimensions of L, right? It has dimensions of L, and Vx, of course, is the average velocity in the x direction. We are now only going to talk about one directional or one dimensional flow taking place, so that it's relatively easy for us to handle this. Okay. Any questions before we move on? No questions. Okay. So now this hydrodynamic dispersion, like I said, is this alpha L times Vx. Now this alpha L is a product of, or okay, I shouldn't say product, is an outcome of the length that the contaminant is going to get dispersed over a certain time duration, right? So what people typically do is that depending on the length that the contaminant has traveled, you can come up with some kind of a empirical expression for this alpha L. Okay, so sometimes people say if the contaminant has moved by a distance L, then the longitudinal dispersion or the longitudinal dispersivity is 10% of L, or 0.1 times L. Okay, there are other expressions available. Like I'll just write down one that's available in the literature. Of course, this is an empirical equation. Okay, so don't take it. It's not something that you need to memorize. Okay, so it's 0.0175 times L to the power 1.46, something like that. Okay, there are other empirical expressions available, like what is this? 0.83 times log L to the power 2.414, something like this. Okay, so basically what it is telling us is that the extent of dispersion depends on the length of travel. Okay, the longer the contaminant travels, the more it is expected to disperse. That's what all of these expressions are saying, right? The first one, the simplest one, is to say it's 10% of the total distance traveled, or the by the average contaminant, 10% of 10% of that. The next one is giving it a power, right? So the longer L is, the more alpha L will be. So it doesn't increase proportionately; it increases more than it's some kind of a non-linear relationship. Similarly, the next one has got a logarithmic term, and then it's raised to some power. Okay, so this is as far as the longitudinal dispersion is concerned. Now the transverse dispersivity, okay, that's referred to as alpha T. So this is the transverse dispersivity. Okay, so transverse dispersivity is basically the dispersion that happens to the contaminant in a direction orthogonal or perpendicular to the direction of flow. Okay, so this one is typically ranging between, let's say, alpha L by 100 to alpha L by 10, right? So it's 1/10 of the longitudinal dispersivity, or maybe 1/100th of the longitudinal dispersivity. This is the typical range of values that the transverse dispersivity can take. Okay. Any questions before we move on? All right. So this is a very kind of a dry topic. So it's there's going to be a lot of terminologies, new terminologies that you will encounter, and then of course there's also going to be uh, some of these empirical expressions. Of course, you're not expected to memorize any of this, but just keep it in mind. Okay. All right. So now, when I'm looking at transport of these contaminants, what we can say is that the total mass that moves, that the contaminant is getting transported. So let's say the total mass flux. Okay, so the total mass flux is basically a combination of the flux that gets transported by advection, so F advection, and the portion that gets transported by dispersion. Okay, now I'm going to call it dispersion with the understanding that it incorporates the effects of diffusion into it, right? Just like we spoke about it just a couple of slides back. So we have like hydrodynamic dispersion, which is a combination of mechanical dispersion and molecular diffusion. Now, those two, molecular diffusion, relatively speaking, is so small in comparison to dispersion that we can, for all practical purposes, ignore it. But of course, if the situation demands, then we might have to account for diffusion also in addition to it. Okay, it depends on the relative magnitude of that. But broadly speaking, I can say that the total mass that is getting transported, the total mass of the contaminant that is getting transported, is the sum of the mass that gets transported due to advection and the mass that gets transported due to dispersion. Now, this advection, like we said, is due to the velocity of the different part of the particles that are getting transported. So F advection. So what will the dimensions of this be? It will be mass per unit area per unit time, right? So if I were to write the advective mass that is getting transported, that would be Q times C. So now, what are the dimensions of Q? The Darcy velocity. Darcy velocity LT minus 1, and concentration will be M L minus 3 kg per meter cube, mg per liter, and so on. So when you multiply these two, you get M L minus 2 T minus 1, right? So it's going to give me units of mass per unit cross-sectional area per unit time, right? Or in other words, what is the relationship between my Darcy velocity and the pore velocity? Remember, the transport is happening through the velocity with which the actual water is moving. Remember, my Darcy velocity, although it is called velocity, it is not representing the velocity of the actual water particles, because the transport is only happening through the movement of the water particles, right? So the pore water will have a velocity which is related to q, but it is not equal to q. So it will be, remember, pore water velocity v is equal to q by n, right? So if I replace that over here, so q is nothing but n times v, or vx, let's say, just to be consistent with what we wrote in the previous slide. So n times vx, assuming the flow is predominantly or only in the x direction, n times vx times c. This is my advective flux. Okay, I'll just take one more minute and then I'll stop with that. Okay. Now the dispersive flux is going to be, like we said, it's going to be proportional to this minus dou c by dou x, right? The concentration gradient, right? Similar to whatever we had. So I will say is equal to minus d times dou c by dou x. Now, again, here you have to be careful, because this equation can work perfectly well whether this contamination is happening through surface water or groundwater or air pollution, whatever it is, right? But when it comes to groundwater, because remember, we are still talking in the context of groundwater, we have to keep in mind that this transport of the contaminant is not happening through the entire cross-sectional area. It is only happening through the portion where the water is moving, which is only the porosity, right? The entire cross section of a soil sample is not transporting the contaminant. The contaminant transport is happening only through the portion of the area where the water is moving. And what portion of the area is the water moving through? It is only moving through the porosity of that particular soil sample. So you'll have to multiply this also by porosity in order to get the actual flux that is getting transported by dispersion. So the total flux F, I'll write it over here, is basically N times Vx times C plus this term. Of course, there is a minus here, so I'll write minus N times D times dou C by dou X. So this is my expression for the total flux that is moving due to these two processes at direction. That's the first term, N times Vx times C, the concentration, and then the portion that is moving because of dispersion, which is minus N times D, which is the dispersion coefficient, times dou C by dou X. Okay, we'll stop with that, and then we'll continue in the next lecture. So you guys are going to be around on Friday, or what's the plan? Let me know. Go ahead. You'll be here on Friday?
So many people are going.
Sorry, can't hear you.
Can you hear?
Go ahead.
So many people are going home actually.
Okay, so basically no class on Friday.
Okay, so
No, I'm asking. I'm not saying. Hey, Srividya, you have not registered for this course. Okay. You have a class here. That's okay. All right. That's okay. So basically no class on Friday. All right. Happy Deepavali to all of you. All right. Take care, guys. Happy Diwali to everybody.
continuing our course, right, sir? So we had to come here.
Continuing my course. What?
I mean, you're not continuing to teach us WRE.
Okay.
So I just came by here. We
No,
had
I
a
know
class.
you have a class here. I know that. Don't make up stuff. Chalo, anyway, all right. Safe Diwali to all of you. Have fun. Chalo, take care. Bye bye. Oh, so when do we meet next? When does the midsem break end? Does it end on Tuesday or
So Tuesday is holiday.
Tuesday is
Midsum
a
break.
holiday? So we'll meet next Wednesday. So 1 week from now we'll meet.
Yes, sir.
Okay, that's fine. No problem. Have fun, everybody. Chalo, bye bye.